Current climatic changes are threatening a severe increase in temperature over the next 3 decades. Increasing temperature raises plant susceptibility to drought and depletes the soil's nutrients. These abiotic stressors will negatively impact a plant's health and overall growth measures. With farmers already struggling to combat inflation associated with fertilizer and chemical pesticides, it is imperative to find a sustainable, low-cost method to maintain the health of crops. Scientists have created a buzz around the potential of using a bacterium as a soil inoculant that forms a symbiosis with the host plant, combating against abiotic stressors, also known as plant growth-promoting bacterium. Compelling evidence suggests Pseudomonas fluorescens may represent an important plant growth-promoting bacteria that can be applied in abiotic stress conditions. This research aims to further explore this possibility in drought and nitrogen-depleted growth conditions to determine the impact of Pseudomonas fluorescens on various growth mechanisms. It was hypothesized that Pseudomonas fluorescens would produce indole acetic acid and promote plant growth in response to stress. To evaluate its potential as a plant growth-promoting bacteria, the production of indole acetic acid by Pseudomonas fluorescens was examined using Salkowski's test and compared to the positive control P. polygma. After germination under normal conditions, Pseudomonas fluorescens in the positive control were applied to their corresponding sprout samples, while the negative control was excluded. After the bacterial application, the sprouts were exposed to their respective stress models 24 hours later. Moderate and high drought stress was induced by applying 88 millimolar and 176 millimolar mannitol broth respectively. The reduced nitrogen stress model employed mulch as a means of nitrogen absorption. After 13 days of growth, half of the sprouts were subjected to crude protein extraction for SDS page and 2D electrophoresis, while the other half were dried for glucosinolate extraction. The extraction of glucosinolates was carried out using a cold methanol extraction method, followed by the desulfation of glucosinolates. The analysis was performed on an ultra-performance liquid chromatography system using Synagrin as an internal standard. Both P. fluorescens and P. polygma synthesize indole acetic acid. Quantification of indole acetic acid from a standard curve and an unpaired t-test determined that P. fluorescens produced significantly more indole acetic acid in comparison to P. polygma. P. fluorescens' ability to produce significantly more indole acetic acid than a well-known plant growth-promoting bacteria further appraised the capacity of using this bacterium as a plant growth-promoting bacteria. With this confirmation, stress models were evaluated to determine their effect on plant height. Results demonstrated that Pseudomonas fluorescens did not further augment high drought. A one-sample t-test was conducted to observe significance between the change in plantlet height in the high drought model compared to their respective control group. Statistical analysis determined that both the negative control and the positive control experienced a significant decrease in plant height compared to their control. Applying P. fluorescens in a high drought stress model did not significantly change plantlet height. In the case of both 2D electrophoresis and analysis of glucosinolates, results were largely inconclusive. P. fluorescens demonstrated its remarkable potential as a plant growth promoting bacteria as it produced higher levels of indole acetic acid than the positive control. Moreover, in the high drought stress model, compelling evidence was gathered suggesting P. fluorescens provided protective measures towards the plant, slowing the impact. There was no significance in the reduced nitrogen and moderate drought treatment conditions. It was unforeseen that there was no significant change in the nitrogen-depleted stress model. This insignificance raised concerns about the validity of using mulch to tie up access to nitrogen. It was anticipated that there would be visual confirmation of soil depletion, such as change in color. This was not the case. Future studies should focus on enhancing the accuracy and reliability of the nitrogen depletion model. For example, employ a nitrogen-free media followed by the introduction of known quantities of nitrogen to achieve better control of the experimental conditions. The results from both the 2D electrophoresis and glucosinolates analysis were inconclusive. A Rubisco standard should be included in future 2D electrophoresis experiments as a comparative measure. Although direct conclusions could not be drawn from glucosinolate analysis, the correct gradient profile and mobile phases were chosen as Synagrin was successfully eluded. Future replication of this analysis would encourage the following gradient profile in combination with the external standard as well as an internal standard. I am profoundly grateful to Dr. Jessica Livingston, Dr. Michael Gibson, Marla McKenzie, and Crystal McFadgen for their unwavering support and unparalleled expertise during my research. Their invaluable contributions have been instrumental in guiding me through the challenges of my study, and their continuous support has been a driving force behind my success. I express my deepest appreciation for their dedication and assistance throughout this journey.